In this lecture, we are going to look at how to use ARIMA in code. For the first few ARIMA lectures, we'll continue looking at the airline passengers dataset to build your intuition on how ARIMA works, and then to cap off this section, we will return to looking at stocks. So in this lecture, we will focus solely on airline passengers, since using this dataset, it will be much easier to understand the behavior of ARIMA under different P, D, and Q values. With stocks, this is kind of difficult, because you can't really tell if there's a problem due to bad settings, or if it's simply due to the inherent randomness in stock prices themselves. So hopefully that makes sense for you. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So we're going to start by re-downloading our airline passengers CSV. Next, we import pandas, numpy, and matplotlib. Next, we're going to load in our CSV using pd.readCSV. Next, we do a df.head just to remind you of what's in our data frame. Next, we do a df.plot to remind you what our dataset looks like. Next, we're going to calculate the first difference in our data. Note that previously, we used the shift function and the subtract operation manually. However, this can also be done by simply calling the diff function. As noted earlier, lots of pandas functionality has been built explicitly for statistical time series analysis and finance, so it's not surprising that such a function exists. Next, we do a df.plot, so you can see what the first difference of the time series looks like. As you can see, it's not quite stationary because there is some seasonality and the variation is increasing over time. Next, we're going to compute the log of the passengers column by calling np.log on the passengers column. Next, we plot the log passengers column. Notice something interesting about this, which is that the values don't seem to be growing as rapidly as they were in the non-logged time series. Furthermore, the amplitude of the cycles looks more constant than it was before. Next, we're going to import the ARIMA class from stats models. Next, we're going to set the frequency of our data frame index to months. And we're also going to split our data into train and test using the last 12 months of our dataset as the test set. Next, we're going to test an AR1 model. This is a model in which the current value in the time series depends linearly on just the previous value. As you recall, this is equivalent to ARIMA 100. Next, we call ARIMA.fit. As with Holt-Winters, this returns an ARIMA result object. Unlike scikit-learn, this does not return a model. Next, we call ARIMA result.predict to obtain the training predictions. We'll place this in a new column in our data frame called AR1. Next, we'll plot the passengers column along with the AR1 column to see how well our model fits with the data. So as you can see, we get this kind of delayed behavior, which should remind you of what happened with Holt-Winters. As you recall, this is how Holt-Winters also behaved when the model was misspecified. In these cases, it seems like the best your model can do is to just copy the previous value or close to it. Next, we're going to grab our out-of-sample predictions by calling ARIMA result.forecast for n test steps. Note that this returns multiple things, unlike the whole winters model. It returns the forecast, obviously, along with the standard error and the confidence intervals. We'll see how we can make use of these confidence intervals very shortly. But for now, let's just plot the AR1 column again against the passengers data. As you can see, this model is not very good. In fact, it doesn't even capture the fact that the data is trending upwards. Instead, the forecast is going in completely the wrong direction. So even a naive forecast would be better than this. Next, we're going to write a function that will plot the fitted values of an ARIMA model along with the forecast and confidence intervals. This will be helpful for the rest of this script so that we don't have to keep writing this code over and over again. So this function takes in one argument, which is an ARIMA result object. Inside the function, the first thing we do is set the size of the plot, which will be 10 columns and 5 rows. Next, we call the plot function, passing in the passengers column of the data frame. This will plot the true data. Next, we're going to obtain the train predictions by calling result.fittedValues. Then we will plot the train predictions by calling the plot function again, passing in the train index, along with the train predictions we just obtained. We'll make this plot green, and we'll give it the label fitted. Next, we will plot the forecast. To start, we need to call result.forecast for n test steps. This gives us back the forecast itself, the standard error, and the confidence interval. Next, we will call the plot function again, this time passing in the test index, along with the forecast values. We'll give this the label forecast. Next, in order to plot the confidence bounds, we'll use the function fillBetween. The arguments to this will be the test index once again, the confidence interval return value at column 0, the confidence return value at column 1, the color red, and alpha equals 0.3 to set the transparency. If you want to double check that the confidence interval return value is actually formatted this way, you're encouraged to check the documentation. Lastly, we call ax.legend so that the legend will show up in our plot. Alright, so in this next block, we're going to test the function we just created, passing in the ARIMA result object we got back earlier. Okay, so this is our AR1 forecast again. Not very good, but we have many options to try next. Next, we're going to try something which I think should be pretty natural for most machine learning people. If our model is bad, why not simply add more inputs? And so in this next block, we're going to use an AR10 model. Luckily, there's not much more work to do beyond what we've already done. We start by creating another ARIMA object with the order 1000. Next, we call ARIMA.fit, and then we pass the ARIMA result into our plotting function. So let's run this. Okay, and we see that this does in fact do a much better job. The first thing we notice is that it does not have the lagging characteristic that the previous AR1 model had. This suggests that the model is actually learning to anticipate the pattern rather than just copying the last value. If we look at the forecast, we see that the model really does learn that the signal is periodic. Unfortunately, it seems to underestimate the true value significantly. Next, we're going to test an MA1 model. As you recall, this is equivalent to ARIMA 001. As before, we can just repeat the same code from earlier. So let's run this. Okay, so this looks pretty bad. It's clear that the MA1 model does not work. In fact, it's even worse than AR1. As you recall, the moving average model's expected forecast is always a constant value, so intuitively we know that this is probably not the right choice. Alright, so next we're going to investigate using the log passengers. Let's begin by taking the first difference of the log passengers. Again, we use the diff function. Next, we plot the first difference of the log passengers. As you can see, the behavior is indeed what we expected. Unlike the first difference of the non-logged passengers, these values do not seem to grow that much over time. Alright, so next, before we do anything with the logged passengers, I want to fit a new model on the non-logged passengers. We know that differencing is good because it at least seems to remove the trend. So for this model, I'm going to use ARIMA 811. I've chosen p equals 8, since it seems like regression on more past values helps. I've chosen d equals 1, since as we saw, this removes the trend from the time series. And I've chosen q equals 1 for good measure, just so that we have a full ARIMA model with all the components. Now, in order to plot the results from this ARIMA, we're going to need to create a new function. Why? The reason why is because we've differenced our data. As you recall, when we difference our data, this removes one row from our dataset, specifically the first row. Each point in the differenced time series is the current value minus the last value. But for the first row, there is no last value, and therefore that value can't exist. You'll see that if you try to use the previous function that we wrote for plotting the results, you will get an error. You are strongly encouraged to try it yourself and to see what the error actually is. Okay, so this function is called plot fit and forecast int. It now takes in 3 arguments instead of just 1. First, it takes in the ARIMA results object, same as before. Second, it takes in a value for d. D will represent the first row in the difference time series that actually exists. Third, we have an argument called call, which will tell us which column of the data frame we fit the model on. That will either be passengers or log passengers. Of course, we have to choose the appropriate one in order to plot the correct data with the model predictions. Inside the function, we first plot the data. This looks the same as before, except now we index the data frame using the call argument rather than a fixed column name. Next, we grab our training predictions using the predict function. I've used the predict function so that we can be explicit about our indices, but also because it's necessary in order to get the values back in terms of the original time series rather than the differenced time series. Notice that for the start argument, I've passed in train.index indexed at d. Before, this value would have just been 0 instead of d. Also notice this third argument type. For this argument, if we pass in the string levels, this will return the model predictions in terms of the original time series rather than the differenced time series. Remember that internally, we are actually fitting an ARIMA model on the differenced time series. So the type argument, instead of predicting the difference time series, actually accumulates back to the original level. Next, we call the plot function for the predictions. Again, notice that for the index, I'm only passing in the values from the dth row onward. Next, we plot the forecast. This part is the same as before. We call the forecast function for n-test time steps. Then we call the plot function to plot the forecast. Then we call the fill between function to plot the confidence interval. Lastly, we call the legend function to show the legend. Next, we're going to call our function, which will plot the results. Okay, so as you can see, this does pretty well. Better than a purely autoregressive model. The train fit is pretty good, and the forecast captures the seasonality, although it seems to underestimate the peak and overestimate the trough. Next, what I want to do is create a function that plots the fit of our model on the differenced series. As you know, this is what stats models is doing internally. In order to show us the final forecast, it's actually taking the predictions on the differenced series and then accumulating them to show us the final non-differenced forecast. So this plot is something you might want to look at if you want to know how well the ARIMA part of the model fits, and that's the part of the model that actually contains the parameters. So first, notice that this function takes in the same arguments as the previous function, a results object, the value of d, which is the offset to skip over the NaN values, and the column name. Inside the function, we first call predict to get the predictions. Note that this time, we do not pass in type equals levels. Instead, we will leave the type as the default value, which will return whatever actually got fitted with the ARIMA model after differencing. Alternatively, you could have just called the attribute fitted values, but I think this is better for understanding what's happening under the hood. Next, we take the difference in the data frame. Now, if you want it to be really correct, you could difference this d times, but I didn't since we already know that d is 1. Next, we plot the differenced time series, along with the train predictions. Then we call our function on our results. Again, this is for ARIMA 811 on the non-logged passengers. Okay, so you can see that these results are pretty good. The dataset is not stationary, and the variance is increasing over time. However, the model seems to capture this, at least for the in-sample data. Next, we fit an ARIMA model with the same P, D, and Q values, except this time we use the logged dataset. As usual, we call fit, and then we plot the results. Alright, so as you can see, our model does pretty well, maybe even better than the previous model on the non-logged dataset. Next, we call our plot difference function on the logged passengers model. So we see that the model again fits pretty well to the detrended time series. This time, the variance does not increase over time, so maybe the model has an easier time learning. Finally, just out of curiosity, I wanted to fit another model on the logged passengers dataset, this time with P equals 12 and Q equals 0. The reason I chose 12 here is because that's the length of the period. So it might make sense to use data from all 12 months over the past year in order to make a prediction. Okay, so this is the same code as before, except now the ARIMA order is 1210. So let's run this. Note that this might take a while, since the algorithm used to train ARIMA is not a closed form equation. Okay, so what do we see? Well, it seems like this is our best model so far. Now, in order to really know how well these models have performed, it would be useful to look at a metric, such as the root mean squared error. So next we're going to define such a function. This will take in 2 arguments, the ARIMA results object, and a flag to tell us whether the model was fitted on the logged passengers or the non-logged passengers. Inside the function, we call result.forecast to get the forecast. Next we check isLogged. If isLogged is true, then we exponentiate the forecast to put the data back into the original scale. Finally, we assign the passengers column of the test data frame to a variable called t. Then we assign the forecast to a variable called y. Then we apply our usual formula for the root mean squared error, and then we return this value. Alright, so in the next block, we compare the root mean squared error for the last 3 models we created. These are ARIMA 811 on the raw dataset, ARIMA 811 on the log dataset, and ARIMA 1210 on the log dataset. So let's run this. Okay, so what do we see? Firstly, our suspicions were correct. Logging the data first does in fact help the model learn the detrended series better. Both ARIMA models have the exact same order, but the version fitted to the log passengers achieves a smaller error. Next, we see that adding more lagged values to the autoregressive part of the model does really help. ARIMA 1210 achieves the best accuracy compared to the other two by far.